Hello, hello, and today I have another math puzzle from Zach Wisner-Gross and the Fiddler. I think I'm going to keep doing these unless I think of something better to do every week. So, feel free to comment with suggestions of other types of puzzles that you might want to see instead of these. But I like doing them, so I think there is an audience of people that want to see these. But if that's not your cup of tea, obviously feel free to skip these videos. But anyway, this puzzle involves going from the start to the finish in corners of a chessboard with a little bit of a caveat, right? So the way to make this puzzle interesting, because if this weren't true, you just go along the diagonal, is that along the dark squares, you're going to move slower than along the white squares. So you're making this trade-off between going the shortest distance along the black squares and adding a little bit of distance, but increasing the speed on the white squares. And so, in theory, I could take any kind of winding path along this chessboard, but it hopefully is somewhat obvious that that's not going to be the most efficient way. And in fact, within a particular square, there's no reason to not take the shortest distance because you're moving at the same speed. And so as I move kind of from one edge of the square to the other, I'm definitely going to do a straight line path between edges of the square. Now that path may kink as I go across different squares, but I'm never going to have to worry about curving as I go along. So this problem is going to reduce, and first just note that the ratio of speeds that we're going to use here is that on white squares, we're going to move at a speed of 1, and on black squares, we're going to move at a speed of 0.9. It doesn't really matter what the units are on those. All that matters is the ratio for the purposes of this problem. So this problem reduces to something like this, where I have some distance x. I'm going to move along. I'm going to move away from the center on this first leg of the journey, and some other distance y for when I intersect at the next kind of spot between squares, and then I'm going to get to the finish. Now I could, you might think, well, why am I going up here instead of to the right? Of course, you could go to the right instead of up, and you end up with an exactly symmetric problem, and you end up with the exact same distance and the exact same time. It would be the exact same. I'm assuming that we're going to move up from the diagonal instead of to the right from the diagonal, but this problem is exactly the same either way you go. And I'm certainly not going to zigzag across the diagonal. That just isn't going to be efficient. So it reduces to something like this. And the next thing to realize here is that actually it's even a little simpler than this. I actually know that x and y are going to be the same here. I'm going to gloss over the mathematical proof of this a little bit to just try to give you a little bit of intuition for why this is true. So it has to do with the symmetry of the problem, right? Now, when I first thought through this, I thought, well, the point of symmetry is that if I go from the start to the finish or the finish to the start, that's really the same problem. So x and y need to be the same. And that's not quite right. Because if going from the finish to the start, you can think of a different way this problem might be set up where, those are still the same problem, but you still want different values of x and y and just that if you're going from the finish to start, those would just switch places and it would still be okay. So the real way you should think about the symmetry of this problem is that I can actually think about x in terms of y and y in terms of x, and those two problems are symmetric. So in other words, if I want to go from, if I fix y at some particular value, and I want to go between the start and y, then I can think about choosing x to kind of optimize my time from getting from the start to y. And similarly, I can think about, for a given x, optimizing my y path, right? So going from x to the finish, there's some optimal y I could choose to minimize my time to get there. And those two problems are exactly symmetric. And because of that, x and y are going to have to end up being the same value. So I can simplify this even further so that I only have one variable x, and I'm trying to choose the x such that my path from the start to the finish is as short in time as possible. So to figure out what the time is going to be, first I need to figure out the distance. And so the distance of each leg of this journey is going to come from Pythagorean's theorem, remembering that the length of any square edge is 1, then the legs along the black square are going to have a distance of square root of 1 plus x squared. and my distance along the white square is going to be you can think of that as an isosceles right triangle with legs 1 minus x, then the hypotenuse is going to have a distance of 1 minus x times square root of 2. So to turn that into a time, I'm going to take those square root of 1 plus x squared values. I'm going to double it because I have two of them. I'm going to divide by 0.9 because that's the speed at which I can travel over those distances. And to get a time, I'm going to take the distance and divide it by the speed. And I'm going to add to that just the length of the journey across the white square because the speed there is 1. So I'm really dividing that by 1. I just didn't include it here. So that is going to be the term that tells me the time it takes to get from the start to finish along this path. And I want to minimize that. So how do I minimize that? Well, the basic way to minimize a function of x is to just take the partial derivative. And note, though, that we are going to be limited in our domain between 0 and 1. Right? If x gets smaller than 0 or greater than 1, that doesn't really represent this problem anymore. And so if my solution ends up in there, I could have some problems. So if I take this partial derivative, set it equal to 0, and then I'll either be at a minimum or a maximum. Talk a little bit about that in a second. But for now, just assume it's going to be the minimum. And we're just going to solve this for x. And so how do I take the derivative of that function? If it's been a while since your calculus class, or if you're just learning calculus, then you may not be familiar with exactly how to do this. And so I'm not going to go into how to take every single part of the derivative, but one important thing that you may have forgotten or not yet learned is this idea of a chain rule. So if I have kind of nested functions that I want to take the derivative of a nested function, but I know the derivative of the individual functions, I can break it out using this chain rule. So in this case, the nested function I'm worried about is this square root of 1 plus x squared. It's not obvious to me how I would just take the derivative of that without the chain rule. And so if I think of g of x as 1 plus x squared and f of x as the square root of x, then I can nest those two things together. So g of x is 1 plus x squared, f of x is square root of x. So f of g of x is the square root of 1 plus x squared. And I can take the derivative of that. That's just going to be the derivative of g of x, which in this case, so g of x, remember, is 1 plus x squared. So the derivative of g is going to be 2x. And multiply that by the derivative of the derivative of f taken at g of x. So f of x, again, is the square root of x. So the derivative of that is 1 over 2 square root of x. And so if I do that all and put it all together, I end up with g prime of x, which is 2 times x, times f prime of x, which is 1 over, so I get this in the denominator, 2 times the square root of 1 plus x squared. And of course, the 2 in the numerator and the denominator can cancel out, and I'm just left with x over square root of 1 plus x squared. Now I can take this and use that to take the derivative of our original function, noting that I have this additional scalar, right, 2 divided by 0.9, that I need to amend to that first term to make it work. And so now when I take this derivative, I get that 2 over 0.9 times the derivative of square root of 1 plus x squared. And I have this extra minus square root of 2 that comes from the derivative of 1 minus x times square root of 2. So if I distribute that square root of 2, I can ignore the scalar, right, the square root of 2, and what I'm left with is the derivative of x times the square root of 2, which is just square root of 2 with the minus sign. So that's what I need to solve for. Bringing that over here, how do I solve that? Well, I can move the square root of 2 to the right and square both sides. That gets me here. I can do a little bit of readjusting. So I'm going to move the denominator on the left over to the right and then divide by 2. And then I can distribute the 0.81 and subtract the x squared terms to get an equation like this. And then, so what does x become here? Is either the square root of 0.81 over 1.19, or if you're like me and want to kind of get rid of those decimals, it's 9 over root 119. And I can take that value of x, plug it into our original equation, I get something like 3.128. Now that is the answer to the problem, but I don't actually know for sure that that's the problem at this point. I do need to be a little bit careful here, because if I go back to my original picture here, right, you'll notice that there are some potential corner solutions. What do I mean by a corner solution? I mean a solution that might be right uh, e- even if it's not, even if the derivative isn't zero, because this problem is on a set domain. So in other words, if x is zero or x is one, I might be at a corner solution. And I also need to worry potentially about the fact that this taking the derivative could be finding a maximum instead of a minimum. So, uh, oops, sorry. So I'm going to look first at the corner solution problem. So if I look at x equals 0, I get that the time taken is about 3.6, which is much bigger than the time that we found before. So that's not a problem. X equals 1 is closer, but still a little bit above 3.128. It's 3.143. So that's not the right solution either. Now, in theory, I would need to worry a little bit about whether or not this is actually a local maximum, right? You could imagine this function might be a squiggly function that kind of goes up and down a lot. And so if I found a local maximum, that might be a problem. Now, because there was only one solution between 0 and 1, and that solution is less than the values of 0, 1, I actually know that's not true. But even just looking at the function, I kind of know that this looks more or less like a parabola. So I also know that if the value I found is less than 2 points, a point to the left and a point to the right, then it's going to be a minimum. But if I wanted to be really careful here, what I would do is I would take a second derivative. So I would take this function that I found originally, 2x over 0.9 times square root of 1 plus x squared minus root 2. And I would take another derivative, get the second derivative of that, and make sure that it's positive. And if I found that, then I would know we're at a minimum, not a maximum. I'm not going to do that because, I don't think it's worthwhile going through that exercise in this video. But if you wanted to be extra careful, that is what you should do. So that is the original problem. There's also an extra credit, which is take a look at an 8x8 board instead of a 2x2 board and do the same thing. Now, you might be thinking, oh, this is just going to be the same problem, but much more tedious. And you're kind of right. But there are some nuances here that I think are interesting that I want to go over. So I'm not going to go through every single step of the solution path here, but I will go over the things that I think are kind of interesting about this problem. So the first thing to know is that on this problem, just like in the smaller version, I'm never going to squiggle around the board on anything but straight line paths that might kink at the boundaries between black and white squares, but otherwise I'm going to have straight line paths. Also, I'm not going to go back and forth across this red diagonal, right? I'm either going to go above it or I'm going to go below it, but I'm never going to go side to side across it because that's just going to make things longer for no obvious benefit. The other thing to note, though, is that actually I'm also never going to go above this red diagonal across the white squares. So if you think about this problem, what it's really entailing, remember, it's trading off distance for speed. So once I get to the white squares, I can go faster, but to get to the white squares, I have to go extra distance. So is that trade-off worth it? And once you cross this new line I've drawn here, that trade-off doesn't even exist anymore. I'm just doing extra distance for no extra speed, right? Because going along the white diagonals kind of maximizes my time on the white squares, maximizes my average speed. There's just no reason to go beyond that. So I'm going to be, assuming I'm going up and not to the right, although if I go to the right, I'll get a very symmetric picture. I'm going to end up in this kind of narrow trapezoid as I go along. And I can similarly argue the symmetric point I made earlier. It'll be even more complicated because there are so many points, but the basic symmetry is going to hold. And so if I think about going from the start to the finish, I'm going to go some distance away from the edge, A, and then, that will continue. I'll go in a little bit from B and then C, and that'll keep going all the way to this value G. And so there are actually only 7 variables. Even though this seems like a much more complicated problem than the 2x2, it's really essentially the same, except that I have 7 variables to care about instead of 1. Now that is a lot. I mean, it gets quite tedious. And if you were to solve this problem like we solved the first, what you could do is, set up those triangles, figure out the distances of each leg in terms of your variables A through G. And then you could take, a partial derivative of every single variable of the time that it would take to traverse all those legs. And so you end up with, seven equations with seven unknowns. It is solvable. But there are a couple things that make this quite hard to solve. The first is that none of these equations have only one variable in them. 5 of them have 3 variables in them, and 2 of them have 2 variables in them. So you can never just get one variable's value outright. What you need, and further, these all have squared terms in them and square roots in them. So you can't just do any kind of linear algebra tricks either. So at least as far as I can tell, the only way to do this is to start with one equation, get, for example, A in terms of B or G in terms of F. You can work from either direction, and then substitute in going backward. And then as you do that, you can get one variable in terms of another, on and on and on, until you get back to the first equation and find that value. And then once you know that value, you can plug that into all the substitute equations you have and get values for all the values between A and G. Now, you definitely should not do this. You should not do this. I did this and I really regret it. Not only is it really tedious and it's easy to make simple mistakes, it doesn't even work. And the reason it doesn't work is because we're actually at a corner solution, right? The way to actually do this is we'll end up at a corner solution, so that the partial derivative trick isn't going to work. Now you kind of have to know that you have to kind of know that you're going to be at a corner solution to know that this is optimal, but there are easier ways to do that than to do all 7 variables like that, which I plan to briefly outline how you would do that. So in order to figure out that we're at a corner solution, what I'm actually want to think about is a smaller problem that's much more tractable to think about, which is, suppose I had these 2 circles, and note that the start on the bottom left is not in a corner, right? It's some distance x from a corner. And so that part is important. But the top right finish point is in a corner, right? So that is going to be in the exact corner. And what I want to think about now is for a given x, so we're going to condition everything that we're going to say on x being a particular value. So x is some number, like let's call x a half. It doesn't matter what you call x, just hold x fixed. If I were to want to minimize my time between that bottom left start point and the top right finish point, what values of y and z would I choose? And now here I can do the 2 equations and 2 unknowns, like I said you should not do in the bigger problem. And the equations are very similar to that, but there's only 2 of them, so it's much easier to go about doing. And if you do that, you will get values of y and z in terms of x. And now the reason I want to focus on this problem, why are we focusing on this problem? This problem will tell you something about what x would need to be in order to end up at a corner solution. In other words, if you find z and y in terms of x, what you can then do is say, okay, what value of x makes z and y exactly 0, right? Makes z and y, or I guess y would be 1 the way I've drawn it here. So z would be 0 and y would be 1. And there will be one exact value of x that will make that work. And what you can then infer from that conclusion is that if my starting point is at that x value or to the left of that, I'm going to end up at a corner solution, right? I'm going to end up in this corner solution, so I don't need to do all these extra partial derivatives and equation solving to get the right answer. And armed with that knowledge, I can then go back to the original problem and think, well, could I end up in a situation like this in a corner solution? And the answer is no, because once you know your x value, and I can't remember exactly what that value is, let's say it was a half, then I know that in the original problem, I'm definitely starting to the right of that, because I'm essentially starting from this picture with an x of 0, right? I'm definitely not to the left of that threshold. And so this kind of a corner solution is not going to be correct. But then I have to wonder, was something like this correct, right? And in principle, there's no reason to believe it couldn't be correct. So you are going to have to try it. But trying this problem is much simpler than the version where you need all 7 variables, because I don't need D, E, F, or G. There's only 3 variables to worry about, A, B, and C. And so I have three variables with three unknowns, sorry, three equations with three unknowns. I'm not going to lie, it's still a bit tedious. You have to do the same at least as far as I can tell, you have to do the same substitution that you would need to do for all seven variables, but there's only three of them. It's a much shorter process, and you can find that. And once you do that, you will find that your value of C, that threshold, is to the left of the threshold you found here, right? And so that will tell you that actually you are correctly assuming to be at a corner solution once you get to here. And so you don't need to worry about, kind of the one step in where the corner solution is only going from like basically the G is one, uh, but the D and E might be, values other than one. So that is, I think, the most efficient way to go about solving this problem. So and that's what I did. Hopefully it's right. If you have any comments on this puzzle or thoughts about other puzzles I should solve, please go ahead and leave them. And thank you for listening. Bye bye.